This is a new project for me, girls. Today we are going to learn about and mind map out, while we're doing it, the electromagnetic spectrum. And the reason we're going to do that is because we did a session on waves. So I know you already know the basics of waves, transverse, longitudinal, and you've got your mind map for there. And then we went on, we looked at atoms with electrons in different energy levels and how the electrons can move up a level and down a level. And when they're excited, they move up a level, they absorb EM radiation, electromagnetic radiation, and when they move down, they emit electromagnetic radiation. So we're sort of coming back round in a loop to waves again, because electromagnetic, the electromagnetic spectrum is to do with electromagnetic waves, which are a group of transverse waves. So let's have a look at that, and then we can sort of bring things around in a circle. So we're going to do the electromagnetic spectrum. And I think I'm going to picture this by doing a long wavelength, which will be like your radio waves, and I go through microwaves that get shorter. Infrared gets shorter still. Visible light, that's what we can see. That turns into ultraviolet, or it's a continuous spectrum. X-rays I literally haven't got any space for, and gamma rays. Okay, so what I'm showing here is an increasing frequency. But actually the wavelength, as you can see, is decreasing. Decreasing wavelength. Does that make sense? Okay, I have scribbled this out, and I've put the arrow in this direction because what we've written is decreasing wavelength, and decreasing wavelength is in this direction. Yes, increasing wavelength, it would be the other direction, but because we've written decreasing wavelength, we're going to scrub that out, and you're going to put your arrow over here. I think what I'm going to do, girls, is just about here, I think is where we said our visible light is. So let's give that a spectrum, because visible light our eyes can detect. So everything else is still there in the spectrum, but visible light our own eyes pick up on, so we can see it essentially, and we can see all these lovely different colours of all their different wavelengths. And you can see that red light over here has got a longer wavelength than, well, I'll come to blue light. Hang on a sec. Where's my blue? Then blue light over here, and that sort of turns into violet, which is on this end of the spectrum. Yeah, so can you see how this is visible light? It's on an electromagnetic spectrum, which is continuous. It starts with long wavelengths over here. I hope I've picturized it okay. I mean, you'll probably do a better job, but they get gradually closer to get smaller, shorter, the wavelengths, therefore closer together. And as they do, the frequency of those waves increases. Yeah, and we'll talk in a minute about how when the frequency increases, the energy that those waves transfer also increases. If we're going to label anything, I'm going to say down here, got our radio waves. This is a bit of an old style radio with a couple of knobs and a speaker and some music coming out. Yeah, that's playing your favourite tunes back in the day, back in the 19 whatevers. And then it moves into microwaves, so you could microwave your dinner. You're probably going to be better than me at finding some space for this. Oh gosh, this is my microwave. There's your big start button. It's got like a dish in it with some food. There's my bowl. God, what is that? Chips? There we go. That's a microwave, okay? So then it's microwaves. Next we've got our infrared. Maybe we can just have that as blaring red. And then infrared merges into the visible light spectrum. So it goes to visible red light through the rainbow of colours. So you can see the wavelength is still gradually decreasing as you go through the visible spectrum. Yeah, this is visible. There we go. It moves into ultraviolet light, which I'm going to just put as UV. And I'm going to put someone with some sunglasses on. Yeah, I would put him sipping a cocktail, but I seem to not have any room whatsoever. But we're just going to give him some shades. And you can sort of picture that anyway, right? You can see the sunshine, you can see light in the sun, but you also know you're going to get a tan. How do you get a tan? You absorb these UV rays, okay? They're slightly higher energy waves than the visible light. All right, then you've got your X-rays. I think we can all do a little skeleton face for that. Okay, you can probably do a better one than me. And then we've got our gamma rays. And this is where we're getting into the topic of radioactivity here. Yeah, these waves are made by changes in the nucleus, which are really hard to make, but changes in the nucleus create these incredibly high energy waves. Yeah, okay. Now, what is the electromagnetic spectrum? Let's make a note, shall we? You know what? I'm going to do it as a rainbow, going around in a circle. Right, so what are electromagnetic waves? They are, I hope you can remember from your waves mind map, they are a group of transverse waves. So we're just going to put a little note there. They are transverse waves. They can also be called electromagnetic radiation. So what does that mean? It means they consist of, they're transverse waves that consist of vibrating okay, let's have a person. Oh, he doesn't look shocked, he looks happy. Okay, he's vibrating. All right, vibrating electric and magnetic fields. I'm pausing just because I'm thinking, how am I going to picturise electric? I think I'm going to have a socket here with a plug thing. That's my electric. Magnetic, I think I'll probably do the standard thing they do, which is your north-south pole, because it allows me to also use red on this side. That's my magnet, yeah? So they consist of vibrating electric and magnetic fields, which is why they can travel through a vacuum, because they don't rely on vibrating matter. Yes, they do not rely on vibrating matter, so they can travel through a vacuum. Why is that important? That's important, girls, because in an exam question, they like to talk about vacuums and they like you to understand whether something can happen in a vacuum or not. It's a concept that comes up a lot in physics. So these waves don't rely on matter and therefore they can travel through a vacuum. Yes? So I'm going to draw... I'm going to draw a vacuum cleaner, but I'm going to speed it up for you. Okay, yeah, that's the worst vacuum cleaner you've ever seen in your life. Colour mine purple because mine is purple. But there's a vacuum cleaner because electromagnetic waves are vibrating electric and magnetic fields. They don't rely on vibrating matter. so they can travel through a vacuum. So why don't we just give this a big fat tick? Yes, they can travel through a vacuum. And why don't we put a big fat cross through matter? Yeah? Boom. Matter's gone. They don't rely on vibrating matter. They can travel through a vacuum. Yes? Right, now here's where this subject ties back to what we were doing about electrons in their energy shells. So here we're going to talk about the generation of electromagnetic waves. Yeah, so the waves can be produced by changes inside atoms, which can either be changes to the arrangement of electrons or changes within the nucleus. Yes, so we're just going to talk about generation of electromagnetic waves. And I think I'm going to draw a little atom. In fact, let's split this in two. So we're going to have electron changes over here. And we're going to have nuclear changes over here. Okay, you know, most of you know, I like to picturise electrons as little dementors. And there are a couple of good reasons for that. So my dementors look, well, very much like black ghosts, to be honest. The reason I picturise electrons as these horrible looking dementors is because they have a charge of what? Think it in your heads. They have a charge of -1. And they don't really weigh anything, do they? 1/2000 to sort of round it up. Their weight is very negligible. And dementors float. They're light. So if you picturise an electron as a dementor, it's got a miserable face because it's negative and it's, you know, it's floating around. It's sort of not really got a mass, so to speak. It's 1/2000 its mass. So that's my little electron. Nuclear changes. Let's just do our standard atom. Put some electrons around the side. So that's my nucleus. So changes in the nucleus emit high energy electromagnetic waves, the nuclei of atoms. Yeah. Now let's picture this out slightly. What are we talking about with electron changes? If I draw a little atom, here are my little dudes. These are my little dementors. That's picturising that these two are floating around in this energy level. It's the first energy level. Now I'm going to have some more dudes. It's very difficult to squeeze in their miserable faces. But yeah. They are in a higher energy level. Why? It's further away from the nucleus. They need more energy to be here, if you remember. These lot are held quite close to the nucleus. What charge is this? Think it in your heads. We've got neutrons, we've got protons in the nucleus. So the only one with a charge is protons, which means that the nucleus is positively charged. Got a positive here. These are our little negatives floating around the edge. So this is a higher energy level further out from the nucleus here. If this atom absorbs a ray of visible light. We're going to have that coming from a sunshine. Because sunshines has all the various different wavelengths. If we look back to our rainbow, it contains all of these in sunlight, in white light. It also contains UV rays up here and infrared rays down there. So we've got electromagnetic radiation. It's coming in from our sunshine. Apologies, I've lost my pen. Here it is. So we'll shorten it. EM radiation or EM waves, same thing. What are they? Transverse waves. Move that down slightly. Transverse waves. I think I'm going to put some fields up here actually. It's a green field. A slightly different colour field. I think I'm going to have a wheat field. Maybe just 2 of these grassy fields. They're my fields, my country fields. So you remember, vibrating fields. So, an atom absorbs energy. The energy is delivered in the form of EM radiation. So that's why I've got our sunshine here. Because that's delivering, it's EM radiation in this case. The EM radiation is coming in and it's hitting this little dimental, my little electron, in a lower energy level, closer to the nucleus here. What happens? My guy gets excited and therefore, and I'm using the correct pen now, okay. This guy is excited. He's had his EM radiation, it's risen his energy, and he's travelled up an energy level. And he's said to be called excited, which is why he looks like this. Unfortunately for him, he cannot stay there forever. And when he drops back down to his original energy level, maybe we'll have him coming around here and have a little parachute on. There. EM radiation comes in. It equals the difference between 2 energy levels. It excites the electron from the low energy level to a higher energy level. And when he drops back down, which unfortunately in every electron's life has to happen, he emits the exact same amount of EM radiation that he absorbed to get there in the first place. So the EM radiation come in equals the EM radiation coming out. So that came in, he got excited. As he dropped back down, he emitted the same amount of EM radiation that he absorbed to get to that place in the first place. So here, what we're picturizing is that electromagnetic radiation or electromagnetic waves are produced when excited electrons fall back down. And that's what he's doing here. He's got a parachute, but essentially he's falling back down to a lower energy level. Yes? I hope that you're drawing your pictures at the same time, otherwise this will be going very slowly. But let's get pictures down on the page because we have time. Let's do it nice and slowly and get it into your head forever. Now, something I need you to understand and know is that different atoms have different energy levels. So there are tons and tons and tons of possible changes that can happen within atoms and molecules. If you think that you've got an atom, but then it might be an atom part of a molecule, and they all have their different energy levels. There are a different combination of molecules. There are so many different, in a particular material, there are so many different atoms and combination of atoms and molecules with their different energy levels, that there are tons of possibilities in terms of the changes that can happen within them, like these electron changes and the energy level moves with different, they've got different amounts of energy between the different levels. So there are so many possible changes that can happen within atoms and molecules, which is why electromagnetic waves produced have a huge range of frequencies. The higher the frequency of an electromagnetic wave, the more energy it transfers. So if we come back here, the higher the frequency, the further up this spectrum here, the more energy it transfers. So why don't we write that in? More energy transferred. And if you're ever in doubt, just remember gamma rays are the highest frequency and they transfer the most energy, which is why they're so damaging up here. So just if you look at it and you're wondering which direction this arrow is going in, remember how much energy these guys have got, the gamma rays up this end. So as you go up, higher frequency, decreasing wave, I've made a mistake there because I put decreasing wavelength, but I've put the arrow this end. Full marks for anyone who noticed my stupid error. If we're going in this direction, the wavelength is decreasing. So scribble that out. And here, as you go up, wavelengths get shorter. Energy transferred increases, yes? And you remember that gamma rays transfer the most energy. So if you can remember that, then you know the arrow goes in this direction. So now we're going to talk about these nuclear changes. So an atomic change that releases a lot of energy will produce a high frequency electromagnetic wave, as we discussed. The gamma rays are high energy electromagnetic waves which come from changes in the nuclei of atoms. Gamma rays are emitted when the nucleus needs to get rid of some extra energy, usually after it has emitted a particle. So we're going to come on to this because this is your radioactivity topic. And it does this by releasing a gamma ray. So all we're going to do for now is we're going to show that nuclear changes, here's your nucleus. It's getting rid of its extra energy in a really high frequency, high energy wave called a gamma ray. And this is usually after it's emitted a particle from the nucleus, which we will come on to as a separate thing. So I just want you to remember, nuclear changes are high energy changes and they emit gamma rays because the nucleus needs to get rid of some extra energy. Right, we're going to come down here and we're going to do a little bit about properties. And there are a few things that you need to remember. So, based on what we were just learning about, Right, properties in here. Just going to move there for you. Right. Here's a key or a key word that I want you to remember. Wide range. So I want you to remember that changes in atoms, so these are both changes in atoms. Changes in atoms and nuclei can generate radiations over a wide frequency range. Maybe we'll put a little, actually, maybe we'll put a big F here. That's our frequency. Changes in atoms and nuclei generate radiations over a wide frequency range and can be caused by absorption of a range of radiations. So if we come back up here, due to the number of energy changes that can happen in atoms, different molecules, there's a whole range of different frequencies of electromagnetic radiation, because this is what we're talking about. We're talking about different wavelengths, different frequencies. And this is a range. There's a huge range of EM radiation that changes in atoms can generate by absorbing a huge range of electromagnetic radiation. Does that make sense? So we're going to say that they absorb a wide range. That's another atom again. And they generate radiations, you could say EM, radiations, of a wide range of what? Frequencies. And then look, you can look up here. This is increasing frequency. This is a continuous spectrum. We call that microwaves, we call that infrared, we call this visible, but it's continuous spectrum. There's no kind of like cut-off point, that's this, cut-off. We just, at some point, in terms of the frequency and the wavelength, call this visible, we call these UV, we call these X-rays, but the actual spectrum is just one continuous spectrum with the wavelengths decreasing and the frequency increasing. What happens when the frequency increases? More energy is transferred. Gamma rays come from nuclear changes and they're incredibly high energy waves. Yeah? I'd love to be able to draw a Range Rover. And I'm going to try. Yeah, that's not a good picture. That is not a good picture. Okay. Yeah, that's my Range Rover. Now, all electromagnetic waves transfer energy from a source to an absorber. So let's look at that. So now we're talking about, you know what, let me go back to my thick pen. We're talking about energy. A bit thicker. Right. The energy goes from a source to an absorber, which I realise you can't see. There we go. So let's just give some examples of sources. A hot object. What object is hot? Should we have a kettle? Let's have a kettle. Oh Lord, this is challenging me. Is that a kettle? It's got a top like that, right? The little thing. That's the switch. That's a kettle. It can sit on this little thing. And there's its plug. Okay. This is a hot object. Yes, this is my kettle. It's a hot object. The hot object is the source. It transfers what? It transfers energy. Yes? By emitting infrared rays into the surroundings, which means that this is the surroundings are the absorber, yeah? Let me draw some infrared rays off here. Okay. They're not the best infrared rays you've ever seen in your life, but here's your source. It's your hot object. It's transferring what? Energy. By emitting infrared rays. This is your EM, electromagnetic radiation. EM waves, infrared radiation, which is absorbed by the surroundings. So in this particular case, it's infrared electromagnetic radiation, okay? Let's give a different example. I think we'll do a radio. Gosh, here we go again. My two big knobs. This is a very old 1950s radio. This is kind of your source now, but within the radio, it's oscillating electrons actually. That's your source. This is your radio transmitter. These are radio waves. Actually, this is the receiver that I've just drawn here. I'm not really sure how to do the transmitter. Let's just do a little stand like that and the person can be talking here into it. So the person's talking here. They're oscillating electrons at the source, producing radio waves. They transfer energy through these waves to a receiver where it causes the electrons to oscillate. It's an example of how electromagnetic waves transfer energy from a source to an absorber. So we'll remember that for now, and then we'll go into detail on this. So this is electromagnetic waves and energy, and we're talking about them transferring energy from a source to an absorber. And there are various examples. We could do radio waves from the transmitter to the receiver. Maybe we should write that in. And we talk about oscillating electrons in the radio wave case. And this is a receiver. Yeah, now we're talking about matter. When any wave meets a boundary between two different materials, it can be reflected, absorbed, or transmitted. And electromagnetic waves of different wavelengths, because these are all electromagnetic waves, but depending on the wave we're talking about, they have different wavelengths. may be reflected, absorbed, or transmitted differently when they meet a boundary. Also, electromagnetic waves with different wavelengths are refracted by different amounts, because different wavelengths of EM radiation travel at different velocities in different materials, so it leads to like a dispersion or a separating out of the wavelengths, which we'll go into when we go back into waves actually, and we'll do very in detail about refraction and reflection. For now, just in terms of electromagnetic spectrum stuff, let's just make a note of that. So, when they meet a boundary, what's going to be our boundary? I think I might do a brick wall. Yeah, I think I'm going to do a brick wall. Okay, that's our brick wall. That is our boundary. Obviously the boundary is not necessarily, it's not going to be a brick wall, but we're just picturizing a boundary. So you've got one material this side and a different material this side. We're going to call that material 2. Okay, so there's a boundary, but specifically between two different materials. Yes? What happens? It can be okay. It can be reflected. It can be absorbed. Transmitted. And refracted. So I'm going to speed this up and I'm going to do my pictures, and you can as well.